Welcome to ThirdEye Labs, where we make the unseen seen. Today, drawing with math. In 1807, Joseph Fourier handed the French Academy a paper with an outrageous claim. Any curve, however jagged or arbitrary, can be built from smooth waves. The greatest mathematicians alive called it impossible and held his paper back for years. He was right. And today his idea has a party trick. Give Python any drawing, and it will find the hidden circles that recreate it. A star, an eye. By the end of this video, you will know exactly how this works, and you will be able to build it yourself in 30 lines of Python. First, the honest part most tutorials skip. A vector drawing is not a list of XY points. Open the raw SVG file and you find drawing commands. Move here, then bend along a Bezier curve, steered by control points. The file is a recipe. So step 1 is to taste it. We walk along each curve and sample it into dots. Next, the canvas itself becomes the complex plane. Every sampled dot is one number, z equals a plus bi. And here is why we bother. Multiplying z by e to the I theta rotates it. The whole machinery of spinning circles becomes plane multiplication. One more step. Raw samples bunch up unevenly, but the Fourier engine reads the drawing as a melody, one note per beat. So we slide the points until they are evenly spaced along the curve. Now the drawing is a function, z of t, the pen's position at every moment in time. Think of a music box. The song is encoded as bumps on a turning drum. Each bump is a note at a moment in time. Our drawing is now exactly that, a song written in positions instead of pitches, waiting to be decomposed. Here is the bet Fourier made. The pen's journey, z of t, is a sum of terms, and every term is one circle. Ck is a complex number whose size is the circle's radius and whose angle is its starting position, spinning at speed k. If the bet is right, finding the drawing circles means finding these numbers ck. Now the question this whole video hangs on. The drawing is a soup of spinning components, all mixed together. Pause for a second. How would you fish out just one circle? Here are 3 components spinning at speeds 1, 3, and -2. The stroboscope. Multiply the whole soup by e to the -2 pi I3t, spinning everything backwards at speed 3. Watch. Every component shifts speed, and the speed 3 component freezes dead still, while the others keep spinning. Now average over the whole loop. Anything still spinning sweeps a full circle, and a full circle averages to 0. Only the frozen arrow survives, and that survivor is the coefficient C3. Do one stroboscope pass per frequency, and you have the discrete Fourier transform. The formula is nothing but spin backwards and average. That is the entire engine. Sanity check with real numbers. 4 points. 1, I, -1, -I, a tiny diamond. Run the stroboscope at speed 1, every term lands exactly on 1, so the average is 1. A single circle of radius 1, and indeed, these 4 points sit on exactly that circle. The machine works by hand. Run 1 pass per frequency on our eye drawing, sort by radius, and out comes this table. The drawing's DNA, a handful of rows, each one a circle. That is all a drawing is. Here is the promise kept. This is the entire machine, top to bottom. Load the drawing, extract every circle, sort them, and rebuild. 30 lines of NumPy, count them, and not a single signal processing library in sight. Walk it with me. Part 1 loads the points and treats each one as a single complex number. Part 2 is the stroboscope you just watched. For every speed k, spin the whole drawing backwards and take the average. That highlighted line is the formula from a minute ago, character for character. Part 3 sorts the circles, biggest radius first. And Part 4 chains the top 16 circles tip to tail and lets the last one hold the pen. When someone says Python can see a shape, this is everything the word see means. No magic, no black box, a loop, a multiplication, and an average. You could type this from memory tomorrow. Now run the DNA forwards. Chain the circles tip to tail, biggest first, set them spinning at their speeds, and let the last tip hold the pen. The mechanical arm dances, and the drawing re-emerges from pure rotation. How many circles does it take? 1 circle is just a ring. 3 make a blob. 5, and the eye is forming. 20, the error drops under 0.5%. 100, and you cannot tell the copy from the original. The big circles are the skeleton, the tiny ones are the details. One honest caveat: try a square. Near the corners, the reconstruction wiggles and overshoots, and adding more circles squeezes the wiggle thinner but never kills it. This is Gibbs ringing. Smooth curves are cheap, sharp corners are expensive. Remember that, it is about to matter. And now the punchline. Here are the drawing circles as a row of data. Delete the smallest 90%, and the drawing barely flinches. You just watched lossy compression happen. Keep the big frequencies, drop the small. Applied to little blocks of pixels, this exact idea is the soul of JPEG. And this is not a party trick. The keep the big frequencies move compresses your photos and your music. Your inner ear physically performs a frequency decomposition on every sound you hear. And in an eye, convolutions are secretly multiplications in Fourier space. This same engine can even hear, and that is exactly where this series goes next. Where does this go? In the companion lab, we build this whole pipeline in 30 lines of Python. You're drawing in, circles out. Artists already drive motion graphics with equations like these. And the deeper idea, math that can compose images rather than just copy them, is the seed of generative AI. But here is the real test, not a toy shape. A one-line portrait of a girl traced from a real picture into 2048 points and loaded with the exact np.load line from our 30 lines. 200 circles, 1 pen, the bun, the bangs, the eye, the nose, the lips. A face rebuilt from pure rotation. If the engine can draw this, it can draw anything you can. One more loop of the clockwork. Every drawing you have ever made was always this, a chord of circles hiding in plain sight. Math can see. So, in one breath, a drawing is a melody of complex numbers. The Fourier transform is a stroboscope that freezes one circle at a time and reads it off. And keeping only the big circles is both the drawing and the compression that runs your phone. Build it yourself in the lab, and you will never see a drawing the same way again. Next time, we point this same engine at music, isolating the bass, finding the beat, and learning why a full unmix needs an eye. Thanks for watching and keep exploring. Next time, math can hear. Please like and subscribe ThirdEye Labs if you enjoyed this video and let me know in the comments.